So hi, good evening. So can you please confirm if my voice is audible and video is visible? If my screen is visible?
Yes, sir.
Okay, thanks. So we'll just start. So today the portion is mainly based on um, synchronous machines. So we have a set of few problems and a few theoretical questions as well. We'll try to answer that. Okay. So the first question is again very simple. The maximum possible speeds in RPM at which an alternator can be driven to generate voltage at 60 hertz and 50 hertz respectively are dash and dash. So we know that the maximum possible speed is going to be your synchronous speed, which is 120 into F by P, correct? And in order to have maximum NS, it means you need to have minimum number of poles. Obviously, your P should be minimum, and obviously, you know that if we tell minimum number of poles, it means it's a two-pole machine. You cannot go lesser than a two-pole machine, obviously. So if your P is 2, in the first case, when your F is 60 hertz, your maximum speed is going to be 120 into 60 by 2, which would give you how much? 3600 RPM. And in the other case, if you have your frequency to be 50, you would be getting 3000 RPM. So the answer is D. Okay. The maximum possible speed for 60 hertz and 50 hertz is actually corresponding to 3600 and 3000 RPM respectively. Okay. Okay. So we'll go to the next problem. Then in a synchronous generator operating at 0 power factor lagging, the effect of armature reaction is dash. Correct. So they have told that it is 0 power factor lagging. Correct. That is phi is basically 90 degree. Okay. So what would be the effect of armature reaction? Right. So what is armature reaction? Armature reaction is basically the effect of the magnetic field generated by the armature current or the winding current on the rotor field flux. Correct. So armature reaction is the effect of the magnetic field generated by your armature current on the rotor field flux. So now it can have multiple effects, right? So based on the angle or based on the power factor, it can either aid the rotor field flux, right? It can either aid it, which means it can magnetize it, or it can demagnetize it, that is reduce the magnitude, or it can also have cross magnetizing effect, okay, based on the angle, correct? So let me write it over here. That is effect of magnetic field produced by the stator current or armature current produced by armature current on the field flux, right? This is your armature reaction. So you know that there are field windings on the rotor. So rotor field windings, let's say they generate a flux phi f and your stator armature current, right? Stator armature current produces a flux phi A. Now the point is phi F and phi A can interact with each other, correct? Phi F and phi A would kind of interact with each other. So when the current is flowing through the armature, it creates its own magnetic field and this kind of interacts with phi F. Therefore, it would modify your effective phi F, correct? It would modify your effective phi F. So now the point is based on the relation or based on the phase angle between phi F and phi A, you can have three possibilities. One, it can either be cross magnetizing, or it can demagnetize, or it can magnetize. Okay, that is, it can have three effects. One is cross magnetizing effect. The other one is magnetizing effect. The other one is demagnetizing effect. Right? Okay. So based on this, your effective phi, right? That is phi f. Let me call it as phi effective changes. Okay, so we have three effects due to armature reaction. Okay, so let me take a new slide. Okay, so if let's say this is the direction of your terminal voltage, let's call this as VT, right? Now the point is if your armature current is 90-degree lagging, correct? Armature current is, let's say, is 90-degree lagging. Okay, this is your zero power factor lagging condition. ZPF lagging, where your armature current lags voltage by 90-degree. Okay. So your VA is 90-degree lag. Okay. And we also know that your phi F, or that is your rotor flux basically leads. It is over here, phi F, right? So in that scenario, you understand that because your current is lagging, your armature flux is also lagging phi A, correct? So what you would see is that phi effective, since phi F and phi A are in opposite direction, phi effective is going to be phi F minus phi A. So phi effective decreases. Basically, your flux is decreasing, which means that it has a demagnetizing effect. Okay, this is one scenario. The other scenario is you have your VT over here, and let's say your current is let's say your current is 0 power factor leading. Okay, so this is your IA and this is, let's say, your VA. This is your ZPF leading condition. So IA is 90-degree lead. It leads voltage by 90-degree, and your phi effective. So your phi F is something like this. Okay. So what you would see is that your phi effective, because both of them are in the same direction, phi effective is going to be phi F plus phi A, because both phi F and phi A are in the same direction. Therefore, it gives you a magnetizing effect. Right? And lastly, we have this condition that you have unity power factor. So VT is also in this direction. Your IA is also in this direction. Therefore, your phi A or phi A is also in the direction of your VT. And your phi effective, as usual, is over here. So what you would see is that the net value would be somewhere over here. That is the resultant of both phi F and phi A. This would be your phi effective. Okay. So your phi effective is going to be a vector addition phi F plus phi A. Okay. So which means that you're going to get some angle over here, which is a cross magnetizing effect. So this is your unity power factor condition wherein your phi A is equal to 0 degree. Okay. Okay. So this is the effect of armature reaction. That is what is phi effective due to the magnetic field produced by your stator current. So you see the question is synchronous generator operating at ZPF lagging, correct? So 0 power factor lagging means you are over the first scenario, okay? Which means that you are going to have a demagnetizing effect, okay? So you will be having a demagnetizing effect, all right? Okay. So we will move on to the next question. So the next question is the 0 power factor characteristic for the Portier diagram can be obtained by loading the alternator using lamp load, synchronous motor, water load, and DC motor. Okay. So okay. So one thing is that to get 0 power factor, right? To get 0 power factor, we need a load that would draw reactive power, right? Only then we can have something that would kind of give me 0 power factor, right? That is, I want a purely lagging load or a purely leading load, which would give me a phase of plus or minus 90 degrees. To get zero power factor, we need a load that draws reactive power. Correct? So among these, which of these would draw reactive power? One is lamp load, synchronous motor, water load, and DC motor. So obviously, you know that DC motor is not the answer. Correct? DC motor works on the DC scale. We cannot talk about reactive power over there. Right? Water load is not the answer. Lamp load is a purely resistive load. It's a R load. So you cannot draw any reactive power using lamp load. Okay. The answer is synchronous motor. Right? So I can load my synchronous motor because an overexcited synchronous motor behaves as a inductive load. Overexcited synchronous motor behaves as an inductive load. Right? Because to get ZPF, you need something that makes sure, because ZPF, to get ZPF, you need something that makes sure phi is 90-degree lagging. That is current lags voltage by 90-degree. Okay. So water load is R load, DC motor is not an AC load. Okay. Lamp load is purely resistive. So unity power factor. Hmm. Okay. Yeah, sorry. This is um an underexcited synchronous motor. Sorry. An underexcited synchronous motor behaves as an inductive load. Okay. From seeing the options itself, you can tell that obviously lamp load, water load, and DC motor are not the answers, because lamp load is R load and water load is also an R load. Okay. Okay. Because to get ZPF condition, we need a load that draws reactive power. Hmm. Okay. So, okay. So the next question is, a cylindrical rotor synchronous generator will deliver maximum power output when load angle is equal to synchronous impedance angle, load angle is equal to internal power factor angle, load angle equal to 90-degree, and input power factor is unity. What is the answer for this? Okay. What is the answer for this question?
Option C.
Why?
Sir, load angle is equals to the impedance angle.
So that is option A now. So which is correct? Option C or option A?
Option A.
Okay. So where does it come from? How do you tell that it is a correct answer?
Hello, sir.
How?
Good evening, sir.
Yeah, hi.
Sir, for finding the maximum power, we should keep the derivative of maximum power with respect to load
Correct.
angle should be equal to 0, sir.
Correct.
So that to get maximum angle power, we should then find theta s minus load angle should be equal to 0. So
Correct.
if we change, then that is equal to theta s is equal to load angle.
So
That's why
basically your
answer is
dp by d del equal to 0, right?
yes, sir.
dpg is what we call it. Huh. So that should be equal to 0. Then what do you do?
Sir, then we keep the derivative with respect to load angle. Then for maximum power, we get the cosine term of that theta minus L that is equal to 1. Maximum equal to 1. Cosine of that is equal to 1.
Right.
So that's why the cosine of 1 means cos 0 is 1, sir. So that's why theta minus del load angle is equal to 0.
Equal to correct. Correct.
So
Correct.
that gives the option A as the answer, sir.
Correct. Okay. So my point is, people generally think, okay, directly P is equal to, let's say, EV by X sine del. So del is equal to 90 degree. Do not click this answer and come. That is why I was asking. Okay. make sure that you see the other option. Okay. So we'll move to the next question. Then okay, next question is a three-phase synchronous generator is operating at constant load while the excitation is adjusted to give unity power factor current. If the excitation is now increased the power factor, what will happen? So a synchronous generator was operating at some load, and what you did was you kind of adjusted the excitation so that you get unity power factor at the output, unity power factor current. Now the excitation is increased. So what will happen to the power factor? So the question is what happens to the power factor in a synchronous generator if you increase the excitation? So what would happen? Would it be leading? Would it become lagging, or would it not be impacted at all, or it would become zero?
Hello, sir.
Yeah.
Sir, this can be lagging, sir, because at unity power factor, generally we only get the real power. So if
Correct.
we increase the excitation, sir, then it will start to give reactive power as well, sir. And if reactive
Correct.
power comes in, sir, then as it is a synchronous generator, sir, then the inductive load will come into the picture and lagging, it become lagging, sir.
Correct. Correct.
And if we
Correct.
decrease it, sir, actually, if the it will actually supply reactive power to the grid. That's why it's lagging. If we decrease the excitation, sir, then it will become leading as it absorbs the reactive power from the grid.
Correct. Correct. Correct.
Thank you, sir.
So what is happening if you increase your field current, right? That is, you increase your phi f or field current. That is, you increase IF, right? So what happens is your internal EMF is also going to increase. Okay. So then what happens is you already know that E is equal to V plus J into I into X. Correct? So now if E increases, for the same V, your reactive component, that is J into Ix, right? That is your, this part increases. J into X is same. So basically your I increases. Okay. That is your reactive part of your current is basically increasing. Okay. You know that this is the reactive part. So reactive part, and this is a plus J term. So reactive part is basically increasing. Okay. That's why what would happen is that your power factor becomes more and more lagging. Okay. So what would happen in a motor? If let's say the question is synchronous motor. In a synchronous motor, I am increasing the excitation. Excitation increases. Excitation increases. So excitation increases means what will happen? The power factor will be, you see the relation would be reversed, right? Position of E and V are going to get reversed. Therefore, what you will see is that power factor will be leading, right? If it's a synchronous motor, this is a synchronous generator we are talking about, right? So for synchronous motor and synchronous generator, the effect would be exactly opposite. Power factor will be lagging. Is this fine? Hello,
Yes,
is
sir,
this
it is. Yes, sir.
okay?
We got it, sir.
Yeah, so please observe whether it is synchronous generator or synchronous motor before you go ahead. That is the trick. Okay, so we will go ahead with the next question then. The impedance value of a generator is 0.2 per unit on a base value of 11 kV 50 MVA. Right? So basically they have given your S base is 50 MVA and your V base voltage base value is 11 kV. Okay. And what they have given is that the impedance value is 0.2 per unit. Okay. Let's say, okay. So that's it per unit is 0.2. The per unit impedance, or let's call this Z volt. The per unit impedance value for a base of 22 kV, right? So this is all VB1. VB2 is 22 kV and SB2 is 100 MVA. What is your ZPU new? Okay, so we just need to establish the relationship, right? So your Z per unit is proportional to S into
V square.
correct into V square. Okay. No, is it proportional to V square? It is
Inversely proportional, sir.
inversely proportional. Yes, divided by V square. Correct. Dimensionally also you can check it is inversely proportional. Okay. So it is ZPU is proportional to S by V square. Therefore, what you see is that ZPU new over ZPU old is going to be what? S2 divided by S1 into V1 square divided by V2 square, which means that your ZPU new is equal to 0.2 into S2 is 100 MVA divided by S1 is 50 into V1 is 11 square divided by V2 is 22 square. Right? Which gives you 0.2 into 2 into 1 by 2 square. Gives you 0.1 per unit. Okay.
Yes, sir. Got it, sir.
Okay. Okay, this is a very standard question. That is, they give you the base values and ask you to calculate the impedance. That's a very standard question. Okay. A synchronous generator with synchronous reactance of 1.3 per unit is connected to an infinite bus whose voltage is 1 per unit through an equivalent reactance of 0.2 per unit. For maximum output of 1.2 per unit, the alternator EMF in per unit should be dash. Okay, so let's break this down. So first of all, they have given that synchronous reactance of 1.3 per unit. So X is 1.3 per unit. It is connected to an infinite bus whose voltage is 1 per unit. So V is basically 1 per unit. And they have also given that through an equivalent reactance of 0.2 per unit. Okay. So let's say this is Xg is 1.3 per unit. And there is also the line which has a reactance of 0.2 per unit. Okay. We have given that for maximum output of 1.2 per unit, that is your P per unit, right? They are telling P max. So P max is going to be 1.2 per unit. What should be the alternated EMF? What is your E in per unit is the question. Okay. So if I try to represent it, you have an alternator, let's call it E, right? And it has a synchronous reactance. So we call this Xg, and it is connected to an infinite bus through an equivalent reactance of 0.2 per unit. So till this point it's your alternator, and after that you are having your line. So you have a line which is XL, and after that you are having your infinite bus which is V. Okay, what is E? Right, what is E is the question. So you know that basically E is sorry, your P is EV by X sine del. They have told P max, maximum P, which means sine del is going to be 1 or del is 90 degrees. So P max is going to be EV by X, right? That is your P max is 1.2, 1.2 is equal to E into V is 1 divided by what is X? X equivalent, since they are in series, you know that X is going to be Xg plus XL, right? That is 1.3 plus 0.2, which is 1.5 per unit. 1.5 per unit. Therefore, your E is 1.2 multiplied by 1.5, which is
1.8.
1.8. 1.8. Okay. So yeah, it's a very simple question only in the end. So okay, so shall we move ahead to the next question?
Yes, sir.
Okay. Probably we'll be finishing much before time. It's only 7 o'clock right now, and there are only 11 questions in total anyway. Okay, a synchronous condenser is dash. What is a synchronous condenser? An overexcited synchronous motor driving a mechanical load, an ordinary capacitor bank, an overexcited synchronous motor with no shaft extension, an overexcited synchronous motor without mechanical load. So what is synchronous condenser?
Sir, maybe the last one. Sir, without mechanical load.
Okay, so where is it used?
Sir, it is basically used for supplying reactive power to the electrical grid.
To
Power factor
supply
correction.
reactive power. Correct,
Power
correct,
factor
correct.
correction.
Yes, yes. So it is
I heard the
basically
word
like a, yeah,
large capacitor bank, sir. It
yeah,
works
yeah. So it
generally.
is. Mhm.
Sir, it generally
Tell
works like a
me.
large capacitor bank which supplies
Huh?
reactive power to the grid side.
Correct, correct, correct. So since you can control the excitation, it's basically like a controllable capacitor bank, right? Yeah. So so what happens is generally in power systems you have a lot of loads are inductive, right? Like most of the loads are inductive. So what happens is because of these inductive loads which draw a huge amount of current, there will be large voltage drops. Okay. So where the synchronous condenser comes into play is that it injects reactive power. Therefore, what happens is it kind of maintains your voltage, grid voltage. Okay. That is one is for voltage regulation. The other one is, as you were telling, it improves the power factor because again, most of the motors in the industry is draw lagging current, which means there is going to be a power factor. So in order to compensate for that, um, people use this, correct? Synchronous condenser. So one is voltage regulation, generally in transmission systems where you have voltage instability due to inductive current again, and that is a huge current that will be drop. That is to maintain the voltage. And second one is of course to maintain your power factor. Okay. Yeah. So basically reactive power support. And you always know that synchronous motor which is under excited is basically behaving as an inductive load, whereas synchronous motor which is overexcited behaves like a capacitive load. That is, it is able to supply your reactive power. Okay. So I think option D is the answer. Okay, overexcited synchronous motor without mechanical load. However, in the answer key they had supplied that overexcited synchronous motor with no shaft extension. Okay. So as far as my knowledge base goes, it is synchronous motor without mechanical load only. All right.
Yes, sir. Yes, it is correct, sir. Sir, this happens a lot of times, even in assignments also, sir. Whatever answer is
Yes.
correct, but the answer key is saying something else.
Yeah. So I don't know. The point is, I am in no way related to whatever assignments are
Yes, sir.
being provided to you or even the evaluations.
Yes,
So
sir.
I
Yes, sir.
cannot help you out. But
We
I'm
raised
just
we raised this concern in forum a lot of times, sir. Even emailed the same things, but nothing is
okay.
happening, sir.
Okay. Yeah. Most of the times this problem happens. Wait, so let me clarify over here. So the answer is this. So this is yeah. So yeah. Yeah. So synchronous motor, this is fine, and this is demagnetizing is also fine. Yeah. Okay. Yeah. Anyway, so theoretically speaking, conceptually speaking, it is option D only, right? Because synchronous we saw synchronous motor if it is under excited, it draws lagging power factor current, which means it acts as an inductive load. If it is overexcited, it is capacitive load. And because it acts as a capacitor bank. You have so power factor regulation, and the other one is voltage regulation. Okay, fine. So compensates for huge inductive loads. So this compensates for voltage drop in transmission lines. Okay. So the next question is a three-phase star-connected salient pole synchronous generator is driven at a speed slightly less than the synchronous speed with open circuited field winding. So the field winding is open circuited. Its stator is supplied from a balanced three-phase supply. Voltmeter connected across the line gave minimum and maximum readings of 2735 and 2805 volt. The line current varies between 380 amperes and 300 amperes. Find the direct axis synchronous reactance per phase.
Sir, these type of questions we will not get options for it, sir. Everything is fill in the blank.
Most of the numerical problems over here were fill in the blank, apart from the theoretical questions. So
Okay.
you would have, yeah, but sometimes it can be calculation based, sometimes it can be like this, but it is again totally dependent on who is setting the question paper.
So how much part will be numerical, sir? I guess
That
from the
also,
total.
that is also very subjective. We don't know.
Because if all these type of questions come, sir, in exam, it will be very difficult for us to like score
No,
good
it will be
marks
a
there.
mix of both. Obviously, it will be a mix only. But the point is, we can't exactly guess what will be the.
Yes. Okay.
Okay. So the question is find the direct axis synchronous reactance per phase. Now the point is they have given you what is V max, which is 2805 volt, right? And voltmeter is connected across the line, which means it's a line to line voltage, V line to line voltage, because voltmeter is connected across the line, right? It's not phase voltage, it's line to line voltage. Okay. And similarly, they have given Vmin is 2735 volts. Okay. And they have also given your I min is 300 ampere. I max is 380 ampere, right? Okay. So how do you find out XD? XD is basically what? Just in terms of um, your kind of Ohm's law, you get it is going to be V phase voltage divided by the current. Correct? That would be your XD, which means that this is going to be V max phase voltage divided by I min, right? So 2805 by root 3 is going to be your phase voltage, and here you are going to get 300, correct? So let me calculate. So I think it would be somewhere around 5.4.
Yes, sir. It is 5.39 or something coming, sir.
Yeah, 5.398.
Yes.
Okay, so this is 5.398. This is fine. Why is it V max by I min? Why is it not V min by I max? Or when should I use V min by I max? See, the question is, you understand the question, right? Why should I do V max by I min? Why can't I do the other way around, or why can't I use V max by I max or V min by I min? Why? What prompts me to do this? Any answer? Why? Okay. So
Sir,
see,
I
they have
think,
asked for, yeah.
yes, sir. Sir, I think B minimum by I maximum will give us the quadratic axis value reactance.
Correct, 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 correct. Yeah, you're right. So that's what I wanted to tell. So XD is what they have asked, right? That is, rotor is aligned with your D axis. So XD is maximum. Therefore, in order to get maximum XD, you would be getting um, V max divided by I min. But in case they asked for XQ, right? That is, rotor is aligned with your Q axis. So this would be V min by I max. So again, they can ask for anything. So okay.
Sir, is it
Yeah.
B max by I mean, or it is B open by I short circuit?
It is actually V open by I short circuit. Over here,
Yes.
they have given a range. You're right.
Okay.
Over
Okay.
here, they have given a range. So that is why, in that scenario, we are, if they have given a range, in that scenario, we want to, I just want to tell what value you should take over here. It is, of course, VOC by
Okay.
ISC only.
Okay.
Okay. Okay, so next question is a three-phase 3300 volt 50 hertz star connected alternator has an effective resistance of 0.5 ohm per phase. A field current of 30 ampere produces full load current of 180 ampere on short circuit and a line-to-line EMF of 1000 volt on open circuit. Determine the synchronous reactance excess per phase. Okay. So they have given you what is VOC. That is VOC is 1000 volts and it is line to line. Line to line. It's a line to line voltage. Okay. So what is the phase voltage? V phase voltage is going to be directly 1000 over √3 volts. Okay. And they have given that your short circuit current is, which is ISC, is going to be 180 amperes. Right? 180 amperes is your short circuit current. Okay. So what is your impedance then? ZS. ZS is going to be VOC over ISC, right? That is 1000 over √3 divided by 180. Okay. So how much do we get? 1000 by √3.
3.2, sir. 0.2.
Yeah. So we get 3.21. Yeah. So you get 3.208 ohms. Okay. This is your ZS. Okay. They have also given what is your as an alternative effective resistance of 0.5 ohms per phase, right? So they have also given what is R. R is 0.5 ohms per phase. See, this is all per phase we have calculated. So this is 3.208 ohms per phase. Okay. So R per phase is 0.5 ohms. So what is excess then? We know that Z is equal to R plus JX, or magnitude is going to be root over R square plus X square. Therefore, your excess is going to be how much? It is going to be root over Z square minus R square, right? Root over 3.208 square minus 0.5 square. Correct? Yeah, so it is around 3.168 ohms.
Yes, sir.
Okay. Simple, right? So they have given you VOC ISC. If they have given you VOC ISC, you know that from VOC ISC you can calculate what is your Z, right? So Z is calculated. Of course, it should be per phase. So make sure it is 1000 by √3. And they have also given the effective resistance, right? So R phase is given. So from this, you can find out what is excess. That is root over Z square minus R square. This is simple. Right? Okay. So if this is fine, we will move to the next question. That is A 11 kV three-phase star-connected synchronous motor is running in parallel with an infinite bus. Its direct and quadrature axis reactances are 10 ohm and 5 ohm respectively. If the field current is reduced to zero, find the total maximum power per phase. Neglect armature resistance. Okay. Okay. So what they have given, V is basically V is 11 kV. Of course, this is line to line voltage. Therefore, your V phase is 11,000 over root 3 volts. Okay. And it is running in parallel with an infinite bus. Its direct and quadrature axis reactances are 10 ohms and 5 ohms respectively. So XD is 10 ohm, XQ is 5 ohms. Okay. So if the field current is reduced to zero, find the total maximum power per phase in kilowatt. Okay. So for a salient pole mission, what is the power expression? EV by XD sine del plus V square by 2 into 1 by XQ minus 1 by XD sine 2 del. Right? So what is this portion called? So this particular portion is called excitation power. Right? And this particular portion is called reluctance power. Right? Okay. So let me take new slide. Just give me 2 minutes. I'll just have some water and join in 2-3 minutes.
Okay, sir.
Okay, thanks for hanging around. I'll just continue and we will quickly try to finish this question. So this is the last question as I was telling. Yeah. So the question is, a 11 kV three-phase star-connected synchronous motor is running in parallel with an infinite bus. Its direct and quadrature axis synchronous reactances are 10 ohm and 5 ohms respectively. If the field current is reduced to zero, right? Find the total maximum power per phase in kilowatt, neglect armature resistance. Okay. So if it's a cylindrical rotor machine, right? So or cylindrical rotor, you know that P is basically EV by XS sine del. However, for a salient pole mission, P is equal to, wherein you have direct axis and quadrature axis as well. You have P is equal to EV by XD sine del plus V square by 2 into 1 by XQ minus 1 by XD sine 2 del. Correct? So the question is, it's a obviously a salient pole mission because direct and quadrature axis synchronous resistance are also given. Okay. Field current is reduced to zero. If the field current is reduced to zero, it means that your excitation power, right? That is, your excitation power is basically becoming zero. Field current is reduced to zero. Why? So if your field current is reduced to zero, then what happens is basically your E is becoming zero. So field current is reduced to zero means, so if field current is reduced to zero, it means your E is becoming zero, right? If your E is becoming zero, your first part, right, that is EV by X sine del or the excitation power becomes zero. So the question is find the total maximum power per phase. So your P is now going to be, since E is equal to zero, you are going to get V square by 2 into 1 by XQ minus 1 by XD sine 2 del. And they have asked for maximum power, which means that sine 2 del is equal to 1, right? Del is equal to 45 degree. 45 degree sine 2 del equal to 1. So V square by 2 into 1 by XQ minus 1 by XD. Okay. Right? Just what we have done is sine 2 del, right? This particular component sine 2 del equal to 1. Okay. And E is equal to 0 in this particular component. Okay. So Pmax is basically V square by 2 into 1 by XQ minus 1 by XD because sine 2 del is 1 and E is equal to 0. Okay. So P is equal to, or Pmax is equal to, sorry. P square by 2 into 1 by XQ minus 1 by XD. Okay. So V is how much? They have given V phase is 11 kV. So sorry, V line is 11 kV. So V phase is 11 kV by root 3. So 11 kV by root 3, the whole square divided by 2 into XQ is 5 ohm and XD is 10 ohm. Correct? So right? So how much do we get? So we are getting around 2016 kilowatt. Okay. Yeah, we are correct. So 2016 kilowatt. Is this fine? Is this question fine?
Yes, sir.
Okay. So yeah, again, this is a direct question. So just to summarize what we saw today. So this question from the backside. So this question was on a salient pole mission wherein don't forget that if generally also if even a C is non-zero, don't just put EV by XD sin del. If it is a salient pole mission, you will be having reluctance power also. So that component also needs to be taken into account. That is E square by 2 into 1 by x cube minus 1 by XD sin 2 del. Right. And of course, the excitation power is EV by XD sin del. In this particular question, excitation power is 0, which means obviously your E is 0. Okay, and they have also told find out P max. So therefore your sin 2 del is going to be 1, right? Sin 2 del will be 1. So just directly substitute. Okay, and in the earlier question they gave what is VOC, what is ISC. You have to calculate for per phase, and therefore your impedance is going to be VOC by ISC. Your resistance is given per phase, therefore reactance can be easily found out. That is root over Z square minus R square. Okay, and yeah, so to find out XD value, we always take, of course, it is VOC by ISC, but you have to consider the maximum value for XD, right? So V max divided by I min would be XD, whereas XQ would be V min by I max. Okay. Okay. And synchronous condenser is, of course, for reactive power support. Okay, that is, it's an overexcited synchronous motor. If you overexcite the synchronous motor, you basically make it as a capacitive load. Okay, so synchronous condenser is for reactive power support. Okay. And previous questions were also quite simple. They were based on direct application of formulae, and yeah, one question was on the base impedance, that is ZPU is proportional to S by V square, right? So from that you can easily find out. Okay. Yeah, and we saw what is the condition if you kind of overexcite a synchronous motor and overexcite a synchronous generator. The effect is going to be exactly opposite. Overexcited synchronous motor is like a capacitive load, whereas overexcited synchronous generator will be an inductive load. So that we have to remember. Again, it comes from basic expressions. Okay, and yeah, we saw that we get maximum power when load angle is the same as synchronous impedance angle. That is theta equal to del. Don't write del is equal to 90 degree. Okay. So it comes from dPg by d del equal to 0. Okay. And again, to get zero power factor angle, we can use a synchronous motor because an underexcited synchronous motor behaves as an inductive load. Okay. This particular feature has been used in multiple problems, overexcited synchronous motor, underexcited synchronous motor, and so on. So yeah, better to take note of this particular uh, feature. Okay. Yeah, and we also saw a question on armature reaction, probably something similar you can get in your exam as well. That is at zero power factor lagging, you get a demagnetizing effect. That is your net effective flux decreases. If it is 0 power factor leading, you get a magnetizing effect. So this is for ZPF leading, cross magnetizing effect for unity power factor, and demagnetizing effect for ZPF lagging. Okay. And finally, yeah, this is a very standard question in this 120 FYP. Yeah. Okay. So if there are any doubts, you can ask now, or we can conclude for the day. Is this fine for the day? Like any doubts, or we will meet ahead again on Saturday. So on Saturday, there is this extra session where I thought I will solve a few problems on two-port networks. So if you want to attend it, you can attend it on Saturday. I think the time is a little different, so it will be intimated to you via mail. I forgot exactly whether it's 3 to 5 or 4 to 6, but yeah, I think it's coming Saturday. We will see a few problems on two-port networks.
Thank you very much, sir.
Yeah.
Sir, as the exam is approaching very soon on April 24th, I guess the exam will be there. Can you give us some insights on how to prepare for the examination? As introduction to electrical engineering for me has become the whole electrical engineering, sir. Everything is
Yeah,
included. So can you suggest us some ways so that we can prepare in some short duration, like to focus only on the problems or only on the concepts that are given on the lectures, or we should try some other problems as well, sir? So any key tips from you, sir,
Mm,
please.
See, the point is, what I feel is the questions that you are going to get will be very similar to what we have solved over here. So go through all the problems that were solved in your lectures. I think in lectures also, professor is solving a few problems, right? I mean, he's showing a few problems. That you should definitely go through and go through all the problems that we have solved that you have solved in all assignments so far. 12 assignments you have got. So all 12 assignment problems you should be thorough, and you should also be thorough with all the problems that were solved in the class, that is this particular tutorial session. So I think that is enough. So whatever problems would be coming over there, it would be very similar. So any other sources that you are able to find, you can solve them for practice. But yeah, the problems will be similar to how we solved over here.
Thank you very much, sir.
Yeah. Okay. Yeah, so I think two-port networks we will see on Saturday. So if there are no more doubts, we can close for the day. Okay. Yeah, I think that's it.
Thank you very much,
Okay.
sir, for the class.
Yeah, good night,
Thank you.
everyone. Have a great weekend.
Thank you.